Okay, are you able to see the slide?
Yes, sir.
Okay, so this class we are going to look at penalty function method for solving problems with constraints. In the last class we looked at Lagrange multiplier method, but that is only suitable for hand calculations. And in practice, nobody will use Lagrange multiplier method. But these type of numerical methods like penalty function method is used by engineers and scientists to do the constraint optimization problems. This penalty function method is particularly easy to use and it is a favorite method. So first we'll see how to use penalty function methods to solve constraint optimization problems. So this is a very popular method used by practicing engineers and students. And what happens here is that the constraint optimization problem is converted to an equivalent unconstrained optimization problem, okay, by incorporating the constraint as a penalty function into the objective function. So the constraint is embedded in the objective function as a penalty. So now you can use unconstrained methods like Cauchy, Fletcher, etc. to solve the problem. Okay, but it is not very easy to solve the penalty function method, although the formula looks simple. So there is an iterative method or procedure to find the optima. Okay, the background of the method must be well understood. That is, which type of penalty to give. So there are different penalty for equality constraint and inequality constraint, and you have to give the correct penalty. Only then the solution will move to the correct optima. Okay, so penalty function methods. So we are only looking at minimization problems, and the objective and the constraint must be written in the format of g of x is greater than or equal to 0. So in the last slides for Lagrange method, the constraints were written as g of x would be less than or equal to 0. So you have to take the negative of that constraint and you will get g of x is greater than or equal to 0 and h of x is equal to 0, the equality constraint. So how to give the penalty to this? Okay, so what we do is that a penalty is added to the objective function. So now you have to minimize objective function plus r. R is a scaling factor. It will be a number like 1 or 10 or 100 or something like that. And then this is the most important thing. So this is the P of g of x. So P is the penalty for violating the constraint g of x. Okay. So this, okay, so f of x plus this entire term is added. So what is the logic of this penalty function method? Okay, so whenever a constraint is violated, or whenever a constraint is violated, or whenever the optima value is trying to go into the infeasible region, a positive penalty is added to the objective function. So greater the violation, greater is the penalty which is added to the objective function. So when you add a penalty to the objective function, then the algorithm will try to change the direction of its iterative movement. Okay, it will try to move the search into regions of less penalty. Okay, then R is a positive scaling factor which adjusts the penalty. So this R is a scaling factor. So you can give R is equal to 0.001. So then it will reduce the value of this penalty. Or you can give R equal to 10,000. Then it will magnify the value of this penalty. The value of R is given by the user. Okay. So the value of R is also important. So how to give value of R we'll study later. So first we'll study this penalty function. Okay, that is P of G of X. Okay, so the most important thing is like this. That is the objective function plus penalty function must converge to the same optima as the original problem. Otherwise, there is no use in putting the penalty. So by adding the penalty to the objective function, it is distorting the objective function, and we are getting another minimum, which is not the same minima as the original problem. Okay, then it is not good. So the penalty function must be designed in such a way that when it is added to the objective function, the penalty will vanish at the correct optimum. So some scientific method is there. Okay. So this is the importance of the penalty function method. Okay, so suppose these are the contours of your objective function. Okay, so this is the what to say, feasible region. Okay, so suppose initially when you do the iteration, your xy point is here. Okay, so it is out of the feasible region. So a penalty is added to the objective function based on this distance d. So if this distance d is very large, a large penalty is added to the objective function. Then what the algorithm will try to do is that it will try to move in the direction of less penalty, and it will enter the feasible region. So this is just the basic of this logic. So we will look in the next slide for penalty function of various type of constraints. So penalty for various type of constraints. So first is penalty for equality constraint. So that is called parabolic penalty function. That is objective function plus r into h of x the whole square. So h of x is equal to 0 is the equality constraint. Okay, so as long as substitute, when you substitute the right value of x, then h of x must be equal to 0. So the feasible value of x, when it is substituted in h of x, must give h of x is equal to 0. Okay, so penalty is h of x the whole square. Okay, so if h of x is greater than 0 or h of x is less than 0, then h of x the whole square will be added as a positive penalty to the objective function. And that h of x is equal to 0, the penalty will be 0. So this is the line h of x is equal to 0. Okay. So all xy points on this line, all xy points on this line will satisfy h of xy is equal to 0. So now suppose you go either up or down from this. Is okay, h of x is equal to 0 here. So suppose you are going up like this. H of x will be equal to 1, h of x equal to 2, 3, etc. And on the other side, it will be minus 1, minus 2, minus 3, etc. So the farther you move away from your equality constraint, the h of x value will deviate from 0. So what is the penalty here? Penalty is minus 1 squared. It's equal to 1. Okay, so the 1 will be added to the objective function. So f of x plus r into 1. So this is the penalty if your point is here. So suppose your point is here. Okay. So h of x is minus 2. So penalty is minus 2 squared is equal to 4. So if your the point is here, penalty will be f of x plus r into 4. So the further you deviate from the equality constraint, penalty is added to the objective function. So similarly, if you go on the upper side, then it will be 1 squared or 2 squared and 3 squared. Okay. So this positive penalty is added to the objective function, and it will interfere with the minimization of the objective function. So what it will do, what the algorithm will do is it will try to change the direction and come towards the equality constraint. And as you come closer and closer, penalty value will decrease, and you have to continuously monitor the penalty value. So when penalty value becomes 0, it means that you have reached the equality constraint. So this is the logic of equality of penalty function for equality constraints. Okay, next step, absolute value penalty function. So R into absolute value of g of x. So this is called bracket operator penalty function, which is applied for inequality constraint. So inequality constraint must be written in the form g of x is greater than or equal to 0. So if g of x is negative, it means that you have gone out of the feasible region. So meaning of the bracket operator. The penalty is set to 0 if g of x is greater than or equal to 0. Or if your xy point is inside the feasible region, there is no penalty at all. And if your xy value is in the g of x is less than or equal to 0 region, that is infeasible region, then absolute value of g of x will be taken as the penalty. So I will illustrate this with the diagram. So this is your feasible region. Okay. So here g of x is equal to 0. Here g of x is greater than 0. Okay, greater than 0. And here g of x is less than 0. So as long as your xy point is anywhere inside this feasible region, no penalty is added to the objective function. Okay. Now suppose you are going out of the feasible region. Okay. So g of x is equal to -1, g of x is equal to -2, -3, -4. So what is the penalty if your xy point has gone here? Penalty is absolute value of -1 equal to 1. So what is the penalty if your xy point has come here? This absolute value of -2 is equal to 2. And what is the penalty if your xy point has come here? Absolute value of -4 equal to 4. So the f of x plus r into say 4 or 3 or 2 or 1. So this is the objective function plus penalty. So if you take a point here, penalty is very large. So the algorithm will try to change the direction and move this xy point towards the minimizing direction, that is direction of less penalty, and finally it will enter this feasible range. So this is the logic of the bracket operator penalty function. Okay. The meaning of the bracket operator is these 2 points. That is, penalty is set to 0 if the g of x is greater than 0. That is this region, and penalty is r into absolute value of g of x in this region. That is, g of x is less than or equal to 0. So these 2 properties are indicated by this bracket operator. Okay. Indicated by this bracket operator. Okay, then another important thing is that, so this is an example of the exterior type of penalty function. So it acts only when the point is out of the feasible region, exterior to the feasible point. So exterior to the feasible region. So it encourages the point to move towards the feasible region. So once the point enters the feasible region, it has absolutely no penalty. Okay. Okay, then another variation of the bracket operator is, instead of using absolute value of x, absolute value of g of x, you use g of x the whole square. So here the penalty is much more, and probably the convergence is much faster. Okay, so the rules are same. Penalty is set to 0 if g of x is greater than 0. That is, inside the feasible region, there is no penalty. Then penalty is r into gx whole squared if we go out of the feasible region. So suppose this is the feasible region. Okay. So you are going out of the feasible region. So here g of x is equal to 0. So here g of x is -1, -2, -3, etc., -4, etc. So it will be 1 squared. Penalty is -1 squared here. Penalty is -2 squared. Here penalty is -3 squared. Here penalty is -4 squared. So this bracket operator with the square of g of x is following the same concept as the previous bracket operator penalty function, but the values of penalty is much more. Okay, so much more severe penalties are imposed by this square of gx. So it is hoped that the algorithm will more quickly try to move towards the feasible region. Okay, then another penalty function which is used in inequality constraint, but it's not very popular, is the logarithmic penalty function. It is defined as -r into log e to the base, log g of x to the base e. Okay, so how it works is explained in this diagram. So this is the interior of the feasible region. So in the boundary of the feasible region, g of x is equal to 0. As you go inside, g of x is 1, 2, 3, etc. Okay, so at this boundary, so log of, okay, then another important thing is that this okay, this penalty function is defined only in the interior of the feasible region. That is, g of x must be greater than 0. That is because you cannot have log of negative number. You can only have log of positive numbers. So you can take the logarithm of only interior values of the feasible region. So g of x must have positive values. So let us see how this penalty function works. Okay, so this is the point on the boundary of the feasible region, or g of x is equal to 0 here. So minus log of e to the e, g of x. Okay, so minus log 0 to the base e. So what is this value? Okay, so it can be, so you know that e raised to minus infinity is equal to 0. Okay, so log of 0 to the base e is equal to minus infinity. So minus log of 0 to the base e is plus infinity. So no, you will get a value of plus infinity at the boundary. So this is the boundary of the feasible region. This is the interior of the feasible region. So at the boundary of the feasible region, penalty is plus infinity here. And as you go toward the interior of the feasible region, okay, so when g of x is equal to 1, so log 1 to the base e. Okay, so you get 0. So the penalty, the logarithmic penalty for g of x equal to 1 is 0. And as you go in the interior, for g of x equal to 2, the penalty will steadily decrease as you go into the interior of the feasible region. Okay, so That is how the logarithmic penalty for inequality constraint works. So the explanation is given here. G of x is equal to 0. That is on the boundary of the feasible region. Minus log g of x to the base e becomes infinity. Then for g of x is equal to 1, that is inside the feasible region, the log penalty becomes 0, and if it is greater than 1, the log penalty becomes even negative. So it is negative, means it is encouraging the point to go inside. So penalty decreases as we go to the interior of the feasible region. So the logarithmic penalty is an interior type of penalty function. It will allow, or it will force a point to move from the boundary into the interior of the feasible region. Okay, then there's another penalty function which works in the same way as the logarithmic penalty function. So this also works in the interior of the feasible region. So that is called reciprocal penalty function, and the penalty is 1 by g of x. Okay, so you can so defined inside the feasible region, g of x is greater than or equal to 0. So it is only defined for positive value of g of x. At the boundary, g of x is equal to 0. So 1 by g of x is equal to 1 by g of x is equal to 1 by 0 equal to plus infinity. So at the boundary, penalty is plus infinity. Okay. Okay, so let me. Okay, at the boundary, penalty is plus infinity. So as you go in the interior of the feasible region, suppose it is 1, 2, 3, 4, etc. So here penalty will be 1 by 1 is equal to 1. So here penalty will be 1 by 2 is equal to 0.5. Here penalty will be 1 by 4 equal to 0.25. So as you move to the interior of the feasible region, penalty decreases. Okay. So this is the main feature of this reciprocal penalty function. So it is the same concept as the logarithmic penalty function, but this curve is less steep than the curve for the logarithmic penalty function. Okay. So for logarithmic penalty function, the curve will go like this. Okay. So the penalties are changing more drastically with the logarithmic penalty, and more gently with the reciprocal penalty. Okay. So this is an overview of the various type of penalty functions used by engineers and scientists. Okay, then importance of scaling factor in the convergence of the penalty function to the optima. So it can be shown that penalty function methods give the correct optima only for a particular value of R. That is the scaling factor. And that value of R has to be found out analytically or numerically by trial and error. Okay, so now we are writing minimize f of x plus R into penalty function. Okay, penalty function. And we already studied various types of penalty functions. That is reciprocal, logarithmic, then bracket operator, parabolic, etc. So we have not looked at the significance of value of R. So it is found that for a particular optimization problem and for a particular objective function and constraint equations, only at a particular value of R, like say 0.001 or 0.1 or 10 or 100, will this converge to the correct optima as the original problem. So this value of R has to be found by trial and error or analytically. Obviously, nobody will find it analytically. People will only find it by trial and error. But what is the method? So that is what we are going to see. Okay, so in this today's lecture, we'll only look at how to find the value of R for this parabolic penalty function, h of x squared. Okay. So just as an example, suppose I want to minimize this objective function subject to this equality constraint, that is x plus y minus phi is equal to 0. So I have drawn the contour here, and correct answer is x is equal to 2.5, y is equal to 2.5. Okay? 2.5. So that is the correct answer in advance. Okay. X is equal to 2.5, y is equal to 2.5. That is the correct answer. Okay, so we'll try to solve this problem using the penalty function method. First, we look at it analytically so that we can understand the correct value of R. So let us say analytically what is the correct value of R to solve problems with h of x the whole square type of constraint. So we consider this particular problem, this particular worked example, and the following analysis is representative of all problems involving h of x the whole square type of penalty. Okay. So we are looking at only one example, but the result can be generalized to all equality constraints. Okay, so to solve this problem, we write the objective function like this. So this is the objective function plus R into penalty terms. So h of x the whole squared, that is x plus y minus phi the whole square. Okay, so that is this term. Okay. So at the optima x star y star, then the partial first derivative with respect to x is equal to 0. Then partial first derivative with respect to y is equal to 0. So if you differentiate this equation, you will get two equations. Okay, 2 into x minus 4 plus 2r into this equation, and 2 into y minus 4 plus 2r into this equation. So if you how to find the value of r? Actually, you need three equations, okay? Because three unknowns are there. X is unknown, y is unknown, r is unknown. But if you look at this, these two equations for this particular worked example, you can see that x and y are interchangeable in the equations. So the equations are symmetric in x and y. So x minus 4 is occurring here and y minus 4 is occurring here. X plus y minus 5 is occurring here, and x plus y minus 5 is occurring here. So this means that x and y will have same values in the answer. Okay, so that is also clear from the graphical method solution. That is x equal to 2.5, y equal to 2.5. Okay, but now we assume this is unknown. So how can you find the value of r from this? So since we know that x and y has to be same because these two equations are mirror images of x and y, what we can do is that we can remove this equation, and instead of y you can put x here. Instead of y you can put x here. So, okay, then this 2 will cancel. Okay, so from this equation, so we get the solution. X equal to y is equal to pi r plus 4 by 2r plus 1. That is by eliminating either x or y, we get this solution. Okay, pi r plus 1, x equal to y equal to pi r plus 1 by 2r plus 1. Okay, so you can see that when r tends to infinity, r tends to very large values, so this will tend to pi by 2. X equal to y will tend to 2.5, 2.5, which is the correct answer. Okay, we already looked at the contours and we saw that x equal to y is equal to 2.5, 2.5 is the correct answer. So only for very large values of r, it will converge to the correct answer. So that is what is written here. When r tends to infinity, xy tends to 5.2, 5.2, correct optima. So this penalty function will converge to the optima only at large values of r. So generally for parabolic penalty function, large values of r will give the correct results. So how is this done in practice? So the purpose of this analytical the method is just to show that large values of r will lead to convergence of parabolic penalty function. But what is large value of r? Is r 100 or 1000 or 10,000 or more? So depending on the nature of the problem, r will work at 100 or 1000 or 10,000. So that you have to do by trial and error. So in this class we will we look at an example. Okay. Procedure for numerical solution of x minus 4 whole squared plus y minus 4 whole squared. Okay. So answer. Okay, so we know that at r equal to large values of r, the solution will converge. So what we have to do is that we have to start with small values of r equal to 0, 1, 10, 100, 1000, etc. And we have to check the convergence of the solution, and also we have to check if the penalty is becoming 0. Okay. So first you are putting, okay, so this is the combined objective function which we have to minimize. So first you put r is equal to 0. So when you put r equal to 0, this whole constraint will go away. So you minimize this and you get the solution x is equal to 4, y is equal to, obviously. And you have to check the penalty, okay? So, so this entire term is the penalty. This entire term is the penalty term. So this penalty term must tend to 0 when we reach the correct optimum. So penalty term will be 0 here. It will be equal to 0 into okay, 4 plus 4 minus 5 the whole squared. Okay, that is this thing. Okay, so penalty is becoming 0. So then you have to check the constraint violation. Okay, so 4 plus that is h of x. So this x is equal to 4, y is equal to 4, then minus 5. So h of x is equal to 3. Okay, h of x is equal to 3. Actually, h of x must be equal to 0. So constraint violation is plus 3. Okay, so this is not acceptable. First step is not acceptable. So a step is acceptable when both penalty becomes 0 and constraint violation becomes 0. So now penalty has become 0, that is just because r is equal to 0. Okay, it's not because h of x squared is equal to 0. And constraint violation is 3. So this step is not okay. So you have to go to next step. So you put r equal to 0.1. Okay, step by step we are increasing r. So now r is 0.1. So this entire function can be solved by Cauchy's methods or Fletcher-Reeves method. And the starting point you can use 4, 4, because that is the starting point for the previous iteration. Starting point you can use 4, 4. So when you solve this problem with Fletcher-Reeves method or MATLAB F minimum constraint, then you will get next value of x1, y1 as 3.75, 3.75. So you have to check the constraint violation at 3.75. 3.75. How do you check the constraint violation? So this is the equality constraint. Equality constraint is x plus y minus y. It must be equal to 0 if no violation. Okay. Now, but let us substitute this 3.75, 3.75. 3.75 plus 3.75 minus 5, it will give 2.5. So, constraint violation is plus 2.5, and the entire penalty term is 0.625. That is, this entire term will work out to 0.625. Okay. So, constraint violation is there, penalty term is also there. So this step is not satisfactory. So next you put r equal to 1, r equal to 10, etc. Finally you put r equal to 100. So then you get the x5, y5 is 2.5075, 2.5075. Constraint violation is 0.015. Okay, so that is 2.5075, 2.5075 minus 3 equal to 0.015. So constraint violation has become small. Okay, and penalty is 0.0225. So penalty is 100. So what is penalty? That is r into h of x the whole square. So that is equal to 100 into 0.015 whole square. It will give 0.0225. Okay. So penalty and constraint has become very small. Okay. So you can continue some more iterations, right? Iteration number 6 to 7, etc. until this constraint violation and penalties value fall below a tolerance limit. Suppose you set the tolerance limit as 10 raised to minus 3. Then as long as the constraint violation and penalty becomes less than 10 raised to minus 3, the algorithm will stop. And you will reach the correct answer. X is equal to 2.5, y is equal to 2.5. Okay, we can stop this now. So for second assignment, I'll give some MATLAB type of work to try this penalty function. Okay. Okay, we can stop here.
Yes, sir.